Hello, welcome everyone to the analysis seminar. So today it's a great pleasure to have Maxime Fortier Bourque from Université de Montréal. He will speak about extremal length systole on the Bolza surface.
Thanks, Dima.
Yours.
And also thank you to Damir for inviting me, even though I'm one of the organizers. I'm happy to speak. And I'm also glad that there's a lot of people from Laval, because some of the stuff I'll be talking about, I learned while I was a master's student with Tom at Laval. And also, I took my first course about Riemann surfaces with Lynn, so good to see you, Lynn. All right, so the theorem I want to talk about is the following joint work with Didac, Martinez-Granado, and Franco, Vargas, Pallete, which says that in genus 2, the extremal length systole attains a strict local maximum at the Bolza surface, and the value at the Bolza surface is equal to square root of 2. So I don't think I'll have time to explain why it's a strict local maximum, but I'll talk about the calculation of the value square root of 2. But so before I do that, there's lots of terms to define here, among which is extremal length. And to motivate the definition of extremal length, I wanted to talk about other things which might be more familiar. So let me first talk about the systole of a manifold. So if M is, say, a closed Riemannian manifold, then we define the systole of M as the length of a shortest closed curve in M. So it's the inf of the length of gamma as measured with respect to the Riemannian metric. And here I didn't write the metric in the notation, but it's going to come up later. So M is really a pair of a smooth manifold with the Riemannian metric on it. So length of gamma such that gamma is a curve, a closed curve, so a map from the circle to M, and we want it to be non-contractible so that the length is okay. Oops. Okay, so that's the systole, and then we can make an invariant, more interesting invariant from this called the systolic ratio, which I'll denote by SR of M, which is what is defined as the systole of your manifold to the power, raised to the power, the dimension of the manifold M divided by the volume of M. And the advantage of doing this is that this is now a scaling invariant. So there's more chances that it's more suited for optimization problems. And indeed, there's a theorem of Gromov that says that for a large class of manifolds, this is bounded above independently of the manifold and just depending on the dimension. So, so that leads to this isosystolic problem, which asks, what is the maximum of this thing if you fix the underlying manifold? So fix a smooth manifold. Let me call it sigma. And then the question is, what is the supremum of these systolic ratio over Riemannian metrics H on the manifold sigma? So such that H is a Riemannian metric on sigma. oops. So question mark. So, what is the value of the supremum and which metrics realize the supremum if they exist? And so the answers to these questions are only known, in fact, in dimension 2 for 3 cases. So only known if sigma is either the 2 torus, the projective plane, or the Klein bottle. And in all 3 cases, the proof works as follows, or the strategy. Is to solve a simpler problem by fixing the conformal class of H. So first fix the conformal class. Then solve this restricted problem. And then maximize over conformal classes. And so, for these we have, these are our surfaces, and it turns out that the moduli space of conformal classes of metrics on a surface is a finite dimensional thing. So provided we can do the second step, then it's reasonable to expect to be able to do the third step as well. So just as a reminder, what is a conformal class of metrics? Well, we say that 2 Riemannian metrics H and G are conformally equivalent if one is a pointwise rescaling of the other. So if there exists some positive function f from sigma to 0 infinity, a smooth function such that H is just f multiplied by G. Okay, so like I said, a pointwise rescaling with the scaling factor perhaps different from point to point. Okay, so in other words, what's the above strategy is just to rewrite the supremum over all Riemannian metrics of this systolic ratio as a double supremum. So first do a sup over conformal classes. So C a conformal class of metrics of the sup over the matrix H in this conformal class of this systolic ratio. And then it turns out that this inner thing here can be recognized as some sort of extremal length. So I'll write this as, I can write this as sup over C, and I'll just write sup over H and C. So again, the systolic ratio is what is the infimum of lengths of curves squared, and then we divide by area. So I'll write this slightly differently as capital L of gamma, all a certain family of curves. So I'll just define this notation in a second, divided by area of H. So here I've restricted to 2-dimensional manifold sigma because this is the case I'm going to care about. And this also makes sense in higher dimensions, and we can't compute any of these things in higher dimensions, so let's stick to dimension 2. So where what? So gamma all is the family of all non-contractible curves that we're considering. So non-contractible curves. And then what is L? So for any set of curves, gamma, I define capital H, capital L of gamma with respect to H to be just the infimum length in this family. So just inf of the length of gamma with respect to H. So this is just the length of a single curve with respect to the Riemannian metric H, such that gamma is in the family capital gamma. Okay, so in other words, the length of a set of curves is defined as being the shortest length in this set of curves. And just by definition, we have that this thing on the right is, so this ratio here is just the systolic ratio by definition. But we can also consider the same quotient for other sets of curves besides gamma all, and this is what's called extremal length. So this quantity here, including the soup, is called extremal length of the family of all non-contractible curves with respect to the conformal class C. So let me define that. In general. So for some reason, my tablet is lagging extremely. So I hope it's okay. And don't hesitate to ask questions if anything I'm saying doesn't make sense. So what is extremal length? So let C be a conformal class of metrics. So let's say the class of a metric G. On a surface sigma, and then gamma any set of curves in sigma. So they could be closed curves or not, connected or not, doesn't matter. And then we define the extremal length of gamma with respect to the class C. So as the supremum over the conformal class of the same ratio as before. So the length of the family gamma with respect to H, which is the infimum length, squared divided by the area of H. So I mean, that gives you a conformal invariant just because it's maximized over all Riemannian metrics in a given conformal class. It only depends on the conformal class. And it's a useful invariant that was introduced by Alfors and Berling. And it has applications in complex analysis and in many things. But here I should say, so the original definition by Alfors and Berling is a bit different. So here, and you can expect the supremum to be sort of achieved by a sequence of metrics that sort of degenerate in the limit that don't necessarily converge to a metric. But so if you want to hope the supremum to sort of be attained by something, then you can enlarge the family of things that we take the supremum over. So I define this C bar to be sort of a closure in some sense of this conformal class. So it's the set again of multiples of the original metric G, such that now F there's less restrictions. So we allow it to take the value 0, maybe even the value infinity if we want. And we want it to be Borel measurable rather than smooth. And then there's one more condition. For the ratio to make sense, we require that the area of this sort of generalized metric is positive and finite, so that the ratio makes sense. A priori, the length, like all curves could have infinite length, in which case you have infinity divided by something, but we never divide by 0, and we don't have infinity over infinity, so we get a well-defined ratio. Okay, so that's extremal length. So as I said, it's defined as a soup, so it's easy to bound from below. So if I give you any metric in the conformal class, if you can compute the ratio, then it gives you a lower bound on the extremal length. But then how can you actually compute it? And the answer is, I only know of one criterion for computing this, which is called Berling's criterion. So let me give you a definition for stating this. So let H be a generalized metric in the conformal class. So we say that that sigma equipped with this metric is plump. And in the paper, we say evenly covered by shortest curves in gamma, but it's long to write. So here I'll just say plump for gamma. If there exists a set of shortest curves gamma naught, non-empty, these are shortest curves, meaning that so for every curve in there, its length with respect to H achieves the infimum. So therefore it's equal to this capital L, which was defined as the infimum for all gamma in gamma naught. So it's a subset of the shortest curves, those that realize the infimum among the larger family gamma. And then there's another condition. And so for every function phi from sigma to the real numbers, Borel measurable, we have the following implication. So if the integral over gamma of phi, with respect to the Riemannian metric H, so I don't know how to, let's say, with respect to the length element inherited from H, if the integrals over all of these curves is bigger than or equal to 0 for all gamma and gamma naught, then the integral of phi over the whole surface with respect, again, to the metric H is bigger than or equal to 0. So one way to say this is that you can recover the area measure with respect to H from the one-dimensional integrals along these shortest closed curves. So in other words, you can integrate functions by doing Fubini integration sort of against along the closed curves and over the space of curves gamma naught in some sense. Okay, and then what does Berling's criterion say? It says that if you have a generalized metric, which is plump, for gamma, then this metric is extremal, meaning it realized the supremum in the definition of extremal length. So then H is extremal, i.e. That the extremal length of gamma with respect to the conformal class C is equal to the supremum is achieved for this particular metric. So it's just the length of gamma with respect to this metric H squared divided by the area of H. Okay, so that allows you to compute if you can find these plump metrics. Okay, so what are examples of this? So one first example, I think, it's I think it goes back to Groch. So it says that if you have a Euclidean cylinder, and excuse my drawing skills, so this is meant to be a straight Euclidean cylinder, then this is plump. Is plump with respect to, let's say, the set of all non-contractible curves in the cylinder. So those that wrap at least once around the cylinder, or you could just restrict yourself to the curves that wrap once. So here, gamma naught is what? Is just the round circles, these horizontal circles. These are the ones with shortest length with respect to this metric. And it's sort of clear that the cylinder is evenly covered. You can, to compute an integral on the cylinder, you can just integrate along the circles and against the vertical measure. Okay, then second example, sort of related to this, is any flat torus. Is plump. For the set of all non-contractible curves. And again, this is because if a shortest curve in the flat metric is going to be a closed geodesic of minimal length, and then the torus is homogeneous. And it's foliated by closed geodesics of the same length, all parallel to each other. So the picture is sort of like this. You have a parallelogram for your torus, and then the shortest closed curves will fill this up. And again, the area can be recovered by integrating along these geodesics. So what that tells us is that the extremal length of the curve, the set of all curves, it is realized by this metric. In other words, so it's the ratio of length square over area for the flat metric. So it's the systolic ratio of the flat metric. And then, so this is with respect to, a conformal class C, and in each conformal class on the torus, there's a unique up to scaling flat metric in the class C. And so, as I was saying before, if you want to solve the isosystolic problem, it amounts to maximizing this systolic ratio over all metrics, so over all conformal classes, if we do it at the double supremum. So if you compute this quantity, the moduli space of flat tori is the modular curve. So it's very explicit, and it's easy to see that this is maximized at the flat hexagonal torus. Or the regular X torus. So just you take a regular hexagon in the plane and then identify opposite sides together by translations. And so that gives you a very sort of short proof of Löwner's torus inequality, saying that this is the optimizer for the systolic ratio. Okay, and then one last example more relevant to the topic of this talk is the following. So take little k between 0 and 1, and then let's consider the Riemann sphere punctured at 4 points, which emit a reflection symmetry. So it's going to be 4 points along the real line, let's take plus minus 1 and plus minus 1 over k. So here I'm keeping the point at infinity. So there's really just 4 punctures. And then the C is just going to be the conformal class of the Euclidean metric in the plane. And then what is the family that I want to look at? So I have these points, minus 1, 1, oh, put them too far apart. Minus 1 over k, 1 over k. Okay, and I want to consider the curves that are homotopic to this closed curve, alpha surrounding minus 1 and 1. So gamma here is equal to the homotopy class of alpha, which I denote with square bracket against. Okay, so the result is that the extremal length of this thing is equal to a ratio of elliptic integrals. So it's 4 times capital K of little k. So the notation for these elliptic integrals I find to be a bit awful. Just looks a bit strange. So where k, capital K, is the complete elliptic integral of the first kind. So how is it defined? So k of little k is the integral from 0 to 1 of dt over square root of 1 minus t squared times 1 minus k squared t squared. So I need to say what is k prime of k is defined as k of little k prime. And then what is little k prime? It's called the complementary modulus. So little k prime, and it's defined as the square root of 1 minus k squared. Okay, so let's try to unpack this. So why is this true or proof, let's say, of this? So the idea is to consider the map now given, say, zeta in the complement of these 4 points in the plane. We can, so I'm going to say the map that sends zeta to the integral from 0 to zeta of the complex integral now dz over square root of 1 minus z squared, 1 minus k squared, z squared. So I mean, there's some issues here. First of all, the square root is not well defined. It's well defined if I restrict myself to some simply connected set. And also the integral depends on the path, but if I'm restricted to the simply connected set, then it doesn't matter. So the idea is that so you can make sense of this formula if you restrict yourself to the upper half plane, and if you restrict yourself to the lower half plane. And in each case, this gives you a conformal map. And this is the Schwarz-Christoffel formula with angles equal to pi over 2 at the poles, at the points, the 4 punches. So this sends the upper half plane to a rectangle, the lower half plane to the same rectangle. And so together, if you piece these together, that sends conformally our domain to, so let me call the domain sigma to a pillowcase. So send sigma to a pillowcase. So just the double of a Euclidean rectangle punctured at the vertices. And so there's two layers. There's a front and a back. And then it sends, oh, maybe I should draw this in red. It sends the curve, alpha to some curve going around like this. And now this Euclidean metric on this, this pillowcase is clearly plump for the closed UD6 that are horizontal that go around the pillowcase like this. So this is plump for the homodiptic class of alpha, because once again, it's foliated by shortest closed curves. These are all shortest in their homotopy class, and we can recover area by integrating along these curves. Okay, so it means that the extremal length is realized by this metric, and what does it give you? So now so it means the extremal length of alpha is, I should go back to the initial case. So for a Euclidean cylinder, the extremal length is realized by the metric, which means it's length squared over area, which is circumference divided by circumference squared divided by area. And the area is circumference times height. So this gives you the ratio of circumference to height. Or the aspect ratio of your cylinder. So the same is true here. So we get circumference around this pillowcase divided by height. And so what is the circumference? Well, if you look at this, so the elliptic integral here is the integral from 0 to 1 of this thing. So it's really the length of the segment from 0 to 1 with respect to the sort of pullback metric of the Euclidean metric on the pillowcase. So it's just the length of this segment here. So the circumference is 4 times this quantity. So 4 times k of k. And then it turns out that the height is equal to k prime of k. And this is not obvious. This is by a change of variable. So technically, compute the height, what you need to do is to compute the integral from 1 to 1 over k of the square root, 1 over square root of the thing, or the quantity that's under the integrand for k. But then you do a change of variable, and then you can express that as another complete elliptic integral of k prime. Okay, so that's why this is true. Any questions about this? Okay, so I've told you some examples of how to compute extremal length. Okay, 4 punctures not on the circle. Yeah, so someone is asking in the chat, can you do this for 4 punctures not on a circle? And there's, yes, you can. I mean, whenever you have a closed curve separating 2 punctures from 2 others on a 4 times punctured sphere, you can express it as some sort of elliptic, or some ratio of elliptic integrals. And the metric, the optimal metric is always going to be Euclidean, and it's going to, a 4 times punctured sphere is a elliptic, a quotient of a torus by some the elliptic involution, and so the extremal length can be computed as a ratio of some periods of this on this torus. Okay. but in this case, when there's a reflection symmetry, there's sort of nicer, there's a nice identity that we'll use later on. Okay, so I think I've been going quite slow. So I don't know how much I'll have time to say. So what is the extremal length systole? Well, it's the analog of the systole. So here, let's say sigma is a surface equipped with some conformal class of metric. So that's equivalent to fixing a complex structure or a Riemann surface structure on the surface. Then the systolic, the extremal length systole, sorry, of sigma equipped with this conformal structure is defined as analogously as before, but now we replace Riemannian length by extremal length. So infimum of extremal length of a homotopy class gamma with respect to C, such that gamma. And now, so I want to extend the definition. Before we had a closed manifold. Here I want to allow punctures, so not necessarily compact surfaces. And in that case, we want to take gamma, a curve in sigma, which is essential, meaning that it's not contractible to a point or to a puncture. Okay, so I've told you how to compute extremal length in some cases, and then hopefully that can allow you to compute this other invariant, the extremal length systole, so the shortest extremal length of a curve on a Riemann surface. And so maybe to connect this with what I was talking about before, what one can show is that this is bounded below by the supremum in the conformal class of the systolic ratios of the metrics in this conformal class. And so the right-hand side is something that is difficult to compute. I mean, you can compute it for 3 types of surfaces, but even for any Riemann surface of genus 2, there's no explicit calculation of the right-hand side. But we can compute the left-hand side, which gives an upper bound. So that's maybe one sort of application of this stuff. It's something computable, which gives an upper bound on this maximal systolic ratio in a given conformal class. Okay, and here's a lemma concerning this definition is that in the definition, we can restrict ourselves to simple closed curves rather than all closed curves. So the inf is realized by simple closed curves unless sigma is a triply punctured sphere. Say C minus 0, 1. And in that case, if you have a triply punctured sphere, then in that case, the shortest curves are figure 8s around 2 of the punctures. Okay. All right, so now I've told you what extremal length systole is. So now I need to say what the Bolza surface is. So what is the Bolza surface? I'm going to denote it by B. It's the set of x comma y such that x comma y in the Riemann sphere across itself such that y squared is equal to x times x to the power 4 minus 1. So what does this look like? Well, if I take a point X in the complex plane such that the right-hand side is not equal to 0, then there's two corresponding Y's. And so what this looks like is really two, I'm going to do trick. I'm going to make round circles using this tool. So it looks like two complex planes that are glued at infinity, the origin plus or minus 1 and plus or minus I. So because at these points, the right-hand side is equal to 0, and so there's only one Y associated to it. And so they're glued together at these points, but they're glued in a way that if you go around a vertex in one copy, then you reappear on the second copy and vice versa. So it's like a staircase with two levels around each of these points. And then so here we have a hyperelliptic involution. Exchanging these two copies. So it's just the map that sends a pair xy to x minus y. It preserves the equation, and what it does is just switches these two copies. And so what that does is that defines a branch cover, a 2-to-1 branch cover from your genus 2 surface. So maybe it's not obvious from the picture that this is a genus 2 surface, but you can do like Euler characteristic calculation to see that, for example. And yes, so this gives you a branch cover from that onto the plane with critical values equal to these points that I was talking about. So if we puncture the Riemann sphere at the critical values, what we get is what I call O. It's really the same as the regular octahedron. So C minus 0 and these 4 points, plus or minus 1, plus or minus I. And there was also there's a sixth puncture at infinity. And what I'm trying to say is that if we look at one of these planes, under a stereographic projection, it looks like this. So like a sphere with the sort of intersected with the coordinate planes. And then, so we see that this configuration of 6 points, or this sphere with these 6 points marked, is really conformally equivalent to the surface of the regular octahedron. So yeah, so that's why I call it the octahedron. Okay. So now the point is to compute extremal lengths of curves on the Bolza surface. It turns out that it's enough to compute extremal lengths of curves on the quotient regular octahedron. So I have to say this quickly, but on the so every genus 2 surface, this is true for every genus 2 surface, it always has an hyperelliptic involution. The quotient is this sphere with 6 critical values marked. And so what matters here, so here, this is the quotient by this hyperelliptic involution, which you can think of as just rotating around a skewer. So, and maybe pi was a poor choice because it's also rotation by angle pi around the skewer. Anyway, there's 2 types of curves on the genus 2 surface. There are the separating curves and then the non-separating curves. And if you map these under the quotient map pi, then what they map to is the following curve. So if it's non-separating, it maps it to a curve which separates 2 punctures from 4 punctures. So I'm going to call this a 2-4 curve. And this is a non-separating curve. maps to that. And then if I take a separating curve, it maps to a 3-3 curve. And so it turns out that every simple closed curve on a genus 2 surface is preserved, or its homotopy class is preserved by the hyperelliptic involution. So yes. And therefore, so what I'm trying to say is how to compute extremal length of the curves above in terms of the curves below. So let me call the surface above by X and the surface below by Y. So there's two cases. So let me call, in the two cases, let me call the curve upstairs by alpha and downstairs by beta. So I'm just going to give them the same name in the two cases. So for non-samp case, what you get is that the extremal length of the homotopy class of alpha in X is equal to a half of what it is, what the image curve is in Y. And then in the separating case, it's multiplied by a factor of 2 instead. So, I mean, what's going on here is that a separating curve maps in a 2-to-1 fashion to the curves downstairs, whereas for the separating curve, it maps in a 1-to-1 fashion. So if I take the curve beta downstairs, it really has 2 lifts above. And so that's what makes this difference of a factor of 2 in that case. Okay. So this proposition allows us to, it suffices to compute extremal lengths of curves on the regular octahedron, and that allows us to compute their value in the cover of the Bolza surface. And so how do we compute extremal lengths of curves downstairs? Well, we can do it for a few very symmetric curves. So let me outline 2 such curves. So this is what we call an edge curve. And this we call a face curve. So the edge curve is just a curve that goes around one of the edges of the octahedron. And a face curve is a curve that goes around one face of the octahedron. And so it turns out that we can compute the extremal lengths of these curves as ratios of elliptic integrals. So let me just tell you what the result is. The extremal length of the edge curves is equal to 2√2. And the extremal length of a face curve is equal to 6 times the complete elliptic of the elliptic integral of the first kind evaluated at some parameter v divided by the complementary integral, where v is equal to 1 over square root of 27, plus 15√3. And so in the second case, we don't know of an exact formula for what this is, but we can compute it numerically, and it gives 2.799 and so on. And then 2√2 is approximately 2.818. So on the octahedron itself, the face curves are shorter by a tiny bit. So the result is that the extremal length systole of the octahedron punctured at the vertices is equal to this second thing, so the extremal length of the face curves. And then the second shortest thing are the edge curves. And the second shortest are the edge curves. And how we can prove this is by sort of ruling out all other curves and saying other curves have longer extremal length. And to do that, all we need is a lower bound for extremal length. And for computing a lower bound, we just use any metric in the conformal class, and we use the Euclidean metric on the regular octahedron. And that's enough to rule other curves. And then I guess a corollary of this is that the extremal length systole for the Bolza surface itself is equal to the extremal length of the lifts of edge curves. And then because these are 2 4 curves, the extremal length gets divided by 2 in the cover, so that gives square root 2. So I mean, that's why the face curves lose, because these are 3 3 curves. So when we lift them to the Bolza surface, the extremal length gets multiplied by 2. So it gives you 5.5999, which is larger than root 2. And then this was the only sort of candidate that could have beat the edge curves. So I think I'll stop here and take any questions.
Thank you very much, Maxime, for a wonderful talk. So there was a question in the chat, which I missed. Can you do the same for punctures not on a circle?
Yeah, so in general, a 4 times punctured sphere always looks like a twisted pillowcase. So I'm not sure how to draw this. So let me say, so you can obtain it by taking a Euclidean cylinder, and then you want to shut each circle in 2. But so for a rectangular pillowcase, you sort of glue parallel to each other. But if they're shifted with respect to each other, that also gives you, I don't know, it sort of looks like this. So it's a twisted pillowcase. And every 4 times punctured sphere is conformally equivalent to a twisted pillowcase. And so, if I take this curve here, I can express its extremal length as a ratio of certain elliptic integrals. So I take twice the period that I have below, and then I can also look at now. This here is going to be a complex period, and then you can just take the imaginary part to get the height of this thing. So it's really a ratio of one elliptic integral divided by like the imaginary part of some other elliptic integral.
I have a question. So there is a mathematician, Paul Schmutz, in Geneva, who worked a lot, I think in the 90s maybe, on hyperbolic surfaces that maximize length of the shortest closed geodesic, right?
Yes.
So how this is related to what you're doing?
And so among hyperbolic metrics, the optimizer is the Bolza surface, and that's a theorem due to Felix Jenny in the 80s. And then Schmutz gave a second proof of this. He proved that the Bolza surface is the unique local maximizer for the hyperbolic systole. But I guess the systole, I guess you can just say there's inequalities between these invariants in the systole hyperbolic of the, in each conformal class, there's a unique metric of constant curvature. and then the hyperbolic systole. Well, okay.
And will the systolic ratio always be realized by a hyperbolic metric in higher genus? I mean, is it clear? Or
so let me say it like this. So the maximizer of if you restrict to hyperbolic metric, the maximizer of the systolic ratio is the Bolza surface. But we don't know the maximizer among all Riemannian metrics. Like I said, the maximizer is only known for the torus, the projective plane, and the Klein bottle.
But do people, what do people think that suppose you have, I don't know, some arithmetic hyperbolic surface, right, and in certain moduli space, then arithmetic guys tend to be very, very symmetric, so they have lots of shortest closed geodesic. And I think in some papers by Schmutz, right, he was, so it's kind of natural to conjecture that arithmetic surfaces would be perhaps extremal points for like various geometric functionals.
So I mean, there's a sufficient, so it turned out that there's like a partial converse of Berling's criterion. And so there's a sufficient condition if you have a metric which is optimal for the systolic ratio, then it has to be evenly covered by shortest closed curves. And then there's a paper by Calabi which proves properties. So it also shows that if you have like shortest closed curves that, well, let me say, if through a given point there's more than one sort of homotopy class of shortest closed curve that passed through this point, then the different families of shortest closed curves, they're going to intersect at equal angles. And I mean, there's different conditions. So, but among other things, the surface has to be sort of plump. It has to be evenly covered by shortest closed curves, which rules out hyperbolic metrics, because a hyperbolic metric has a unique closed geodesic in each
okay.
class.
So this could be like flat or round with conic singularities.
Exactly.
Okay.
And for the projective plane, the metric is round, but all other examples are flat.
Okay.
But so there's a theorem of Saburo which says that there's no flat metric on the surface of genus 2, which is optimal for the systolic ratio, which means that the optimal surface has to have positive curvature somewhere. Anyway, and there's some pictures in Calabi's paper which from which you can sort of conjecture roughly what the optimal metric looks like in genus 2. So conjecturally, it would be in the conformal class of the Bolza surface, but with positive curvature in certain regions. But not actually round, like variable positive curvature.
Oh. So Victor Calvin, he's in the library, but he's typing in the chat, says, can you say more what happens on flat sphere with 3 punctures, Calabi-Croak sphere?
Well, so here, well, the Calabi-Croak sphere, so it's this systolic ratio thing, I only defined it for non-contractible closed curves, but you can modify the definition to say it's the infimum of lengths of closed GD6. So if you have a smooth Riemannian metric on a sphere, then it always has closed GD6. And so you can try to maximize the same systolic ratio over a Riemannian metric. And there's a conjecture of Calabi-Croak, which says that the optimal metric would be sort of degenerate. It has cone points. It would be a double of a Euclidean triangle. And then here, so the limiting closed GD6 on this thing are, things that go around like this. or yeah, similar to that. And this is a conjecture, still open. I don't know. I mean, this, what I've talked about is not relevant to this stuff, but like for the systolic extremal, extremal length systole of the triply punctured sphere, this we can compute in this paper, and then we show that it's realized by these figure 8 curves, and then the optimal metric or is achieved by so instead of this equilateral triangle, it's a double of a right triangle like this, and then the figure 8 curves in this metric look like that. So I mean, there's really like there's three figure 8s on the 3 times punctured sphere, and for each figure 8, you have a different metric. So if the right angle is a different puncture depending on which figure 8 you take. Yeah, so I don't know if that answers the question.
Well, Victor says thank you.